Hi, Bill Becker here, Honolulu Community College. And this is CSNT228, and we're going to be looking at Chapter 13 here, which covers processes, and Part 1 here, processes and memory. There'll be something about kernel processes and things like that. So let's get started with Chapter 13 here. So today's focus is processes and memory, as I mentioned. So we can find information about running processes in that /proc directory. And I think I mentioned that in the last video, and the /proc file system. And we'll be looking at viewing process informations, the process life cycle, and process states. So quite a bit in this. So we'll see if we can concentrate on some of the important issues. The commands that we'll be looking at, the ps command, ps_tree, top, uptime, free command, and lsof, list open files. Now this is a bit of a review, but it's always good to review some of this. When people talk about Linux, they're usually referring to the operating system that includes the GNU utilities and the Linux kernel. The utilities such as ls, cp, passwd, password, we've been using these all along this semester. But there's also, Linux is the core of the operating system, the kernel. So maybe we can look at a few things about how the kernel operates too. The kernel manages every aspect of the running system. So the important functions of the kernel include managing processes, memory, virtual file systems, networking, and device drivers. And we talked about device drivers last time, devices and device drivers. So the kernel also accepts commands from the user, manages the processes that carry out the commands by accessing various devices. Kernel also provides access to information about active processes through a pseudo file system. That's in that proc directory. There's all these files that they're not real files. It's just placed in there. It's a pseudo file system. Other Linux pseudo file systems include /dev and /sys, which if you look at those files in that system, they're not really taking up any area on a disk. They just provide information about hardware and devices. So the proc directory that we looked at before, and here's an example of it right here. It's a pseudo file system, and the directories match the PIDs of running processes. So if I bring the terminal in right here, I think that's pretty good. I think we can do that. And then if I do an ls on proc, we saw this last time, I believe. I talked a little bit about that. And all of these numbers, these are actually directories in there. And those directories there's one for each running process. In fact, if I was to just take a look at processes, ps-fe, which means look at the processes, I want a full listing of every process on the machine, well, we'd get something like this. And those same numbers we saw as directories in the proc pseudo file system show up here as process IDs of particular processes. So pseudo file system and the processes, there's a one-to-one correlation there. It mentions in the PowerPoint here, and let me see if I can come up a little closer to that. You may be able to see that a little better. It says some files are writable by root, and they can be changed the way the kernel is currently operating. But even if root changes the way it's operating, that it's not persistent. It won't survive a reboot because it's just in memory. It's just in memory. If you ever wanted to make persistent changes, you'd have to actually go to something on a disk, a file on a disk, and etsy/syscontrol.conf, or the files in the etsy/syscontrol.d drop directory. That's where you would make modifications that would persist. In other words, would survive the reboot process. So in the proc directory, some other commands that read current system information files found in the proc directory include the files top, free, mount, umount, and lscpu. We looked at lscpu, I think, in the previous video. Example of important files in the proc directory that report current state of the kernel is proc command line. And that's information that was passed to the kernel during boot. And of course, that would have had to come off of a file somewhere. And so if we were to take a look at that, what we could do is, I'll clear the screen here, and we could just actually do a cat of cmd line command line, and this shows boot image equal HD 0, and this is the place on the disk. This is the name of the boot issue right there. The root's user ID is right here. The crash kernel is automatic resume. So anyway, it has information that was passed to the kernel when it first started, and of course that came from that directory on disk called in the boot directory. That's where a lot of that information comes from. Okay, so that's looking at that command line, and there's information about kernel memory and modules, and I think I showed you that last time. We could take a quick look at, well, let me see. I'll go to the next slide. I think we can do it from there. I think that's the one that shows some of these. Mem info. Okay, let me take a look at that. Let's take a look at that right here. And if I did a sudo and then I did a cat of proc mem info, and I need, oh, I don't think I got that one right. Let me do it again here. There, and this shows you the memory and the various memory usage, and I think we looked at that last time too. But anyway, that's another one of these in the proc file system. There we go. Just wanted to clean up the terminal there. Okay, so let's see. We'll go back to the slides here. The next slide here, it's talking about after the kernel finishes during the boot process, it starts the init process. Traditionally, it was called the init process, which means previous kernels had it that way, and Unix would call it that. CentOS 8, the first process to start, is now called systemd. That's just, they kind of modernized it, and that's what it's called. We'll refer to it, we could refer to it as the init or initial process, but it's systemd. So this systemd then starts up other processes. Processes start other processes are called parent processes, and the processes started by others are called child processes. And they have this PS tree, which will show you that in kind of a graphical mode. I like to do that essentially using just the PS-FE, and let's take a look at that again. If I was to say PS-FE, and that means I want to see all the processes, and I want a full listing. So there's quite a few here. I'm going to go all the way back to the top, and what you're looking at here, here's the first one, and this is that one. Let's see if I can stretch this out a little bit. There, we can see it. You see that? It's process 0, and that's user live systemd in the systemd directory, and it's called systemd. That was the one previously called init. That's process 0. And so it starts up process 1, okay? And then it also gets started up is process 2, which is this k-thread daemon. And the k-thread daemon is a kernel process. It's actually a thread that starts up, and it starts up a lot of different processes. And you'll notice in these processes here, it says, okay, 0 starts 1, 0 starts 2, because it's the parent process ID, right? All right, 2 is started, the thread D, and then this starts up process 3, which is RCU_GP, and then the next, it also starts up 4, and it also starts up 6. Now, these are all started up in parallel, practically at the same time. And you notice that they have brackets around them here, meaning that they're actually kernel threads. They're not true processes. They're started up in memory, but they're essentially they've got a process ID, and they can start other processes, but they're not a true process at this point because nothing's even running yet. It's just getting things loaded up. But though these are kernel threads that are running here. And you'll notice the thread daemon right here is essentially starting all these processes, 10, 11, 12, 13, et cetera, et cetera, et cetera. And it starts up considerable amount here. We're all the way up to 704. And there'll be other processes, other things going on as these things start up, right? So that's the kernel coming to life, so to speak, coming to life. And so each one of these, there's the parent and there's the child process. So all of these will be running. And essentially, after a while, we'll see some of the larger numbers come up, ones that may be starting to come up in user space. So here it's starting up, but each one of these, still the initial process 1 is starting up all of these right here, getting all this started. And eventually it gets into the point, because we have a graphic user interface on this machine, that then right here, user live exec GDM, that's the GNOME display manager, is running the Wayland desktop. So there the desktop starts up, and it gets TTY1. So at this point, we're starting to get to the point where there's user input can be coming up soon. And you notice we're up to process 1462 already, which has started process 1709. All right, and you notice down here, here's live exec, and this is more of these GNOME processes here. 1709 has now started 1855. See, so how one starts another one, or starts a whole series of them, and then starts another one and starts another one. So that's the way the whole Linux kernel starts up. It's all processes, and it all gets put down. It all originates from the single process 0, which is the initial process that gets started. And here's the systemd, which is PID1, is started by that initial process. And if we move all the way up to the very end here, this is all, now at this point, we're getting into user space. Now here's, sysadmin is the user. This is the user that I'm logged in as, same as you have on yours. Sysadmin is a user, okay? And so now this is logged in, and sysadmin, and various things would be running. These are things that I would have been running, but all of this here is part of that graphic user interface starting up. And we come down to the very end. The last process to be run is what? PS-FE. That's the one we're looking at, see? So it started out as the initial process, that systemd process, and started process after process. And to get the whole system running there, including the windowing system with the graphic user interface and all of this stuff, each one of those little pieces of the puzzle, so to speak, is a process running. And they're all running simultaneously, And when they're all running, that's what you think of as Linux. That's what you're doing, is you are essentially interacting with the kernel by way of these processes. Okay, so we had a tour there of the processes on Linux and the number of processes that essentially are running. We'll look at some more of that and more about processes coming up. So the process hierarchy, let's go back to the PowerPoint again. It says after the kernel finishes loading the system D process, the init process, system D, then starts other processes. We just saw that. Processes start other processes are called the parent process, and the processes started are called child processes. Each additional process that gets started is assigned a unique PID, process ID, in order. pst13 is another command similar to what we saw. I prefer to use that one that's easier to track, looking at what process started which process. But you can look at pst13 too, same information. And here they have an example of how, here's the init daemon or the system D, and then it'll start various processes and they'll start other processes. That was that huge tree. This is obviously abbreviated. We saw there was, 1,000 of them. And then there's user login, and then there's the bash shell, and then there's the user processes that I was running. One of them was ps-le. That was the process I was running right here for you. So that's the process hierarchy, the process structure. Viewing the processes, and we can view that same concept that we saw using just ps-fe. They use a ps3-p, and they can have this they call it text art. I don't see all these exactly in order, and they don't put a lot of the initial ones in, those threads. This is just the processes, not all the threads. So here's another example of that process hierarchy. If you look at parent-child relationships, see, here's an example with that tree, PS tree. There's the GNOME terminal, which starts up the bash, which starts up, maybe they're running SU and bash, and then PS tree. So you can see all that. It's worth looking at that. You got to poke around and take a look at that. And here's another drawing of it. System D goes through a lot of processes. There was like 1,000 of them in there. Comes to the login. There's that a GNOME display manager. You see a whole bunch of GDM, okay, and then bash, and then PS tree. So this is very abbreviated. What I like about that PS command, ps-fe, is you see everything. That's the whole works. Another one they can say ps-forest, and that's another one that kind of draws some art and shows the relationship between the parent and child processes. So the process hierarchy, once again, if the system's been running a long time, it may reach the maximum PID. And you saw as they got larger and larger and larger. They may reach the maximum. And the size of that is in procsys kernel PID max. You can go read that. It's a fairly large number. Once maximum PID has been assigned, the system will roll over and continue assigning available PID values from the bottom of the range. And so it'll essentially run through it again, because as processes end, they give up their PID. So the PS command, we looked at that, list processes running on the system. By default, the PS command shows only the user's process running. ps-forest displays some of the text art. There's a couple different ways to display the use the PS command. Traditional Unix option, and that's typically what I use. I just got used to it. -E-F or -FE is typically the way I say it. Dash full and everything. Full listing means all of the information for each entry, and I want to see all of the entries. BSD Unix without a dash is AX, or sometimes AUX, you'll see. PS has been around a long time, has many options. Another one that's good is PS-U, and then you can give it a username. So it's all of the processes running for a particular user. Because if you just say PS-FE, you'll just get the parent and child of the current login. But there might be other processes that are being run. I'll show you that in a minute too when we. So here they do a PSUX, and they pipe it through head-3, and this will give us a display here. An interesting one is stat here, the stat. That's the status of the process. And there's various codes that they have in there. Let me see, what shell, slide do we have here? Let me take a look here. Okay. The options format, we'll come up to that one in a minute there. So we'll take a look at that stat. PSAX, BS style, PSEF, or FE, doesn't matter, it's an option, can go in any order. And then you can grep for a particular entry. One item of interest is the stat or status, or the S of a process. So if we do that with let's go ahead and take a look at that on this, on the big terminal here. And what I'm going to put in here, they're using a PS dash, or they're just going AU. That's that BSD format, and they're just going head. I'll do 10 of them here. And you notice that this column here, now some of this wraps around, but this column here, it says this is GDM, that's that GNOME Display Manager, and it has an S, uppercase S, lowercase s, a L, and a plus. And if you go to the man pages and decode that, you'll see that the S is that it's in interruptible sleep at this point. It's waiting for an event to complete. So it's just waiting. It's probably ran something else, and then it's waiting. And in the lowercase s, it's a session leader. A session leader. And a session leader is a process that essentially is in charge of the login screen or the terminal. So if you start a new terminal and you start up a session, that bash command that you see right there, that bash shell, that's the session leader. So there's other items in the session. If you run some background processes or you run the command top or anything else, they're all part of the session, but that first bash is the session leader. It's the first one in that tree of PIDs, parent and child processes, for that group. And then all of the commands running within that one terminal session it's called a session or session group. Okay, so if I do a PS-E, now in this one here I don't get the, if I want to get that dash UA, I think. This is a nice one that will show over here. This will show some of the, now this is sysadmin, that's the processes I'm running, and we'd have to go way out here to look and see what some of those are, but those are all, a lot of them are part of that, the fact that we're logged into the terminal. The graphic display manager, and there's all kinds of processes that support that. And you notice we have some here, it says S and lowercase l. That means it's sleeping. It's in interruptible sleep, so you can, and it's multi-threaded, and that's why it's got an L on there. So some of these here, here's the bash command that was run just before I ran ps-ua. So that one, it's come back. Here's the prompt, so it's back. And its status right here, it's the session leader. You see that? Because it's the first bash shell that's been run. If I was to run bash again, let's see what it's going to give us this time. And now I run that, do that ps-au again. And you notice that this bash command here, it has an uppercase and lowercase s. The lowercase s is the session leader. The second one I'm running here, beneath that, it's not a session leader. It wasn't the one that was initially started within that terminal, within that group, within that terminal right there. And the ps-au, it has an R, capital R, so uppercase R, running or runnable. So it's a runnable process, and it's the plus sign means it's in the foreground process group. So, and it was in the foreground. See, it was not a background process. So that's the status of the process, and that's kind of interesting to look at. You read about it here, you play around with it a little bit, and you start running processes, and you'll see, now I see how that works. We'll do some more of that. Okay, so let me go back to the studio here, and let's go back to the PowerPoint. So we were looking at that ps-ef, and we were looking at the status in there. One item of interest is the stat or S of a process, and we just talked about that. Process state options. Here's some of those options. I was reading them off, but here they are right here. And there's a few more. You go look that up or Google it, and you'll see those. Where D, it's uninterruptible sleep, usually input, output. R, running or runnable. So that's the various states, the states of the process. Process states and life cycle. The command shell bash displays that's when you first open a terminal and you get I've got it over on the terminal right there, displays a user prompt and waits for commands to be entered. Okay, it reads commands entered from the command line, and that first bash is the session leader. And that whole group that you're running within a terminal is all part of a group. And some of them would be in the foreground group, and they have access to the standard in, standard out, or some of them run in the background and they don't have access to standard out or standard in. They're running in the background doing something else. But you can still signal them to have them either stop or come back to the foreground. Fork and exec. Now that's an interesting one. In fact, that's probably the heart of this whole process a lesson here is fork and exec. So this is how one process, maybe the session leader, calls another process. Fork duplicates the current parent process, creates a duplicate of the memory space of the parent process. Now that's just an interesting way. I always found that kind of interesting, that when you do the fork, it actually duplicates itself. So if it's bash, you get two bashes, but you don't see them. You only see one. Because the new process space inherits the environmental variables of the parent. That's why those environment variables, the prompt command and a lot of things like that, the path, anything that was exported, they get passed into that child process. Sometimes we call them subshells, but it's the child process. And the exec passes control of the new space to the new child process. Now the new child process takes over. And the new child process creates its own local shell variables besides those ones it got from its parent, using the memory space provided. When the parent-child process, when it finishes, the child process sends a signal 17 to the parent process and then terminates. At least that's the way it's supposed to happen. So the parent process waits for the signal until the child process has terminated. The command prompt is not available until the child process terminates. So let's take a look now. I think I put a picture in here. Okay, here it is. Here's an example of that. Here's an example. Here's our parent process, the bash shell right here. Okay, I've got the bash shell running, and let's say I type in and I run a command, let's say the top command. Okay, the top command, when I run that command, any executable that you run, the first thing it'll do, it will run a fork, and it'll start a child process with a different PID, and then here's the parent PID. So here's the parent's, or PID, right, the parent, and then here's the child's PID. So the parent runs a wait, it goes into a wait state, right? It's not a command, it's essentially, the code is running here, and it's running a wait state there. And the child executes whatever was in whatever command was given to it. If it was the top program, it's be running the top program. So let's say we run the top program for a while, and it'll be running. And then when we exit the top program, maybe give it a Control-C or whatever it takes to exit it, then the child program runs an exit code, and the exit code sends a message to the parent. It sends a message to the wait process here, see? Parent's running this wait. And so the exit says, okay, we're done, back to you again. And the parent, with that wait process, it cleans up all the memory and essentially takes care of freeing up the memory that the child process has used. So it essentially cleans up, as they say, and then the parent process resumes again. So that's fork and exec. Now we can actually see that happen here. I think we can do that. Let's see what I've got here. And I've got a shell over here, and I'm gonna run. Yeah, that's what I want to do, and what I want to try to do here, make this a little smaller, and find another window, and have a second window here. So I got two windows going at the same time. See how we can do that here. So let's say that I'm over here running. So now I'm logged in here, right? And I can say ls if I want to see something. And I can do it also over here. But I could also do my clear screen here. If I said ps, it shows just the processes I'm running in this session here, right? But if I say ps-user sysadmin, that's the username that I'm logged in as, and it shows all the processes up here, and this is everything that's got that essentially started our display manager, all that display manager stuff. So we're just interested in, I'm going to do a tail, so last 10 lines. All right, we're just interested in the end here. And I might even do a tail dash 6, let's say, get the last 6 lines. So here we see that there's a bash and another bash and another bash. This one's got 2 of them running. Let's see what's happening over here. I have 2 running here, see? And we can see them on both sides there. This shows them all. I'm going to exit one of these and get it back to the simplest. All right. Now, if I go, if I do my ps-user sysadmin, I should see 2 bashes running. There they are. See that? One of them is running as PID 5454. That would be this one. And the second one is running as PID 6271. That would be this side over here, see? Because if I do this one right here, I see 5454. See, that's this one. I see this on both sides because I said dash U. So, okay, now I'm going to run another program here. I'm going to say top. And I'm running the top program. Now, this is a program, it's not going to just exit. It's going to show me the top processes and the top resource processes. And I'm not really interested in it. I just want to see what's happening over in this shell again. Now, if I go PS and I do the same one with the user, you'll see what's happening here. I'll get it over here a little bit easier to see. We can see that this bash right here, I think I'm going to see if I can do a dash full dash user. Yeah, that's a little better. Because I see that we have our bash shell running, and here's the top program. See that? The top program, here's its PID, 6428, and its parent ID is 5454. That's its parent process ID. Well, parent process ID is 5454. That's this bash shell, because I ran it right here. And the other bash shell is right here. Its process ID is 6271. See? And when I ran PS-FU to see this, that was run as process 6446, 6271. But what we want to look at is what's happening here is that the bash 5454, right now, it's in the background, isn't it? Because we can't interact with it. We don't see the prompt. All we see is this top command running. So at this point, it's essentially that bash right here, it's running, but it's got the wait, it's in the wait state, and it's waiting for an exit. So if I was to come over here and I was to say Control C, okay, it stops. So what happened is when I press Control C, what's happened here is over on this diagram, this is the top program they're running, and then as soon as I press Control C, the exit went up to and sent a message to our parent process. That was the bash shell. See, that's the bash shell waiting here. Exit sends it up to here. It cleans up everything, gets rid of all the memory and everything that was being used by that top command we saw running, and then it continues on its way. So it's back to being the bash shell again. See, it has stopped waiting. And if I come back here, you notice that right now, see, the bash shell is back. And if I say PS, it's back. It's still 5454. It's the original process. So while I was running another command that was essentially, the bash shell was still the session leader, but the other one was in the session group, and so it could take over the terminal, and it was giving output to the terminal. And as soon as we sent it the exit command, it essentially said to bash, okay, I'm done. Here, clean up everything that got started, and you're back on your own again. And then bash is running. So there's that, the fork and exec. And it was an example of that. So you can play around with that, get a couple of terminals going. And all right. Monitoring processes with top. Okay, that's that command I was just playing with. I wasn't explaining it, I was just using it as an example. But the top command is very useful for monitoring processes, system load, CPU, and memory usage in real time. When you call the top command, it's actually that interactive command. And I'm going to set my terminal over to full size here and start that up again so that when we switch back over, you'll see that there are various commands that we can actually hand to the top command while it's running. See if I have some of those in here somewhere. I'm looking at my notes here. But if they show right here, here's the options for controlling it. If I type in L, it'll toggle load statistics or toggle time statistics or memory usage statistics to the top of the line. So let's take a look at that. So I've got top running here, and you notice what it says. Here's the process ID of the user, and here's the process, and there's some other, I'm not going to go into all of this usage here, but here's the percent of CPU time being used and the percent of memory. Those are the two that we're interested in. And this tells you what command it is. The XORG, and that is part of that display manager. That's using most of the memory right now. And up here, we'll see how much free memory we have, how much total memory we have in megabytes. So we got 7 gigs of memory with 4 gigs free and 1.1 gig used. And this much is in buffers or cache, and this is available memory. So this gives you a full report on it. Now, if I was to type in, just while it's running here, because it'll still take input, if I was to type in the T or the, let's do the L, the load, now this puts the load statistics to the top, and it sorts it by load statistics. And if we do the T, it sorts it by time, how much time it's been using. And if we sort it by M, the memory. And so a lot of times you're interested in the memory, so now it's sorted with the highest memory, the GNOME shell, and then XORG, and the GNOME shell. And if I start moving stuff around here, then it's going to use more memory because it takes more resources. And so what we can essentially do there is we can get different statistics from the top command. And I'll let you do the man page and fool around with that. All right. So let's see now. If I do a Control-C, I usually use Control-C, and that gets us out of it. And it sends that signal to it to end. Okay, where are we going here? See, back to the PowerPoints. Okay, so here's some of the options for controlling the time display. So it's running in real time, and while it's running, it'll still take input from standard in. It's written that way, so standard in still will affect it. So useful viewing the process, useful commands for examining processes. PS, and we showed you that one, and PS-FE, PS-tree. LSOF displays open files being used by processes. Now this can be very interesting. So, or being used by various processes or by various people. That's a very interesting one there, because a lot of times you want to know what files are being used by this particular process. So you can try that one. And then the top command, it's active display of running processes sorted by CPU time, or you can change how it's sorted. And you can use Q to quit. I use Control-C, similar, same thing. But it'll respond to the Q for quit too. So here's another interesting one, load averages. Now, the load averages, that's kind of sometimes it's a kind of a curiosity. What do they mean by the load and you'll see that in the top command. Even if you type in something like uptime, you'll get the load average, So the top command or this uptime command will show you 1 minute, 5 minute, and 15 minute load averages. Give the administrator an idea of the current load and how it's been trending over time. Now, what that load actually is, it's the proportional to the number of CPU cores in the system too, but if the load average is greater than 1, let's say you see a load average of 1.5 or a load average of 2, well, it tells how many, on average, how many of the processes are waiting to get onto the CPU. So if the load average is at 0.5, well then nobody's waiting. Nobody's waiting to get to the CPU. If it's over 1, if the load average was 2, you've got 2 processes in line on average waiting to get to the CPU. That's slowing things down. You never want to see that load average go above 1 because then it starts running slow. So if for some reason you have a multi-user system, or it's a e-commerce system or a website or what have you, and the users are mentioning that if the system seems to be running slow, has slow response time, you might go over run top and sort it by load and see which process is using all of that CPU time. So if you know which one's using the CPU time, if you can somehow, maybe you don't need that process, maybe you can kill that process, maybe it's a runaway process of some kind, then you'll essentially give the rest of the system time on the CPU. The load average is equal to the number of CPU cores indicates a fully loaded system. A load greater than the total CPU cores indicates a system that is overloaded. So if you have 4 CPUs or 4 cores and you have a load of 4, well, that's fine, because that means all 4 of them are full up. Any bit more and people are going to have to be wait. So that's a full house at that point. They mention here that with the top command, it'll tell you how many tasks are running, how many are sleeping, and how many zombies you have. It's always kind of interesting that you'll see zombies in the as processes, and that's never a good thing. But they don't really do a lot of harm. These zombies are basically leftover bits of dead processes that haven't been cleaned up properly. A program that creates zombie processes isn't programmed correctly. Programs aren't supposed to let zombies process stick around. Remember when I showed you that slide up there a ways and I had that picture, this one right here? If the child process doesn't call the wait command, or if the parent wait command doesn't clean up the child process, then you're going to get what they call zombie processes. You can't kill the zombie process because it's not running. It's not running. It's just leftover bits of memory. It can be holding process IDs. So if you have something that's not programmed correctly, because people have to program all this stuff, if you have a badly created program that keeps forking, creating child processes, and then the child process down here, it doesn't call the wait, or if it does call the wait doesn't clean up, then eventually you may start running out of process IDs or running out of memory space. They don't take a lot of memory space, but you keep an eye on it. Because if you've installed some new programs and all of a sudden they're zombies, you say, you know something, I better go back and stop that program I just installed, because that must be the one that's not programmed correctly. So, okay, that's last one here is the free command. Shows you how much free memory you have. You have the total memory in the system, the amount used, and the amount that's free. Some of it's shared, some of it's in buffers or cached, and some of it is available. And you're usually looking for how much is available out of the total memory right there. So, there you have it. You've been watching Chapter 13, Part 1, some of these kernel processes, and we got a good look at processes at fork and exec. So, we'll see you next time, and we'll see you in class.